So in this video, we want to calculate the moment of inertia of a solid sphere. So imagine you're having an apple, for example, okay? That's a sphere that's filled with material, so we call that a solid sphere. So the way to do this, as usual, when you want to calculate the moment of inertia of a distribution, of a mass distribution, you first need to calculate the moment of inertia of a tiny element that reflects the symmetry of that distribution and then integrate over the entire surface of, or the area, or the volume, it really depends, or the length of the distribution in order to get the full moment of inertia. So if we have a sphere, the element that we can isolate here that reflects the symmetry of the sphere, or that can enable us to generate the whole structure of the sphere, is a disk, as you can see here. So we are having the sphere. If you imagine taking a knife and slicing an apple, okay, a very thin slice of an apple, then you're having a disk that has a thickness dx. The radius of our disk is small r, and capital R is the radius of the sphere. So we assume that our element is distant x, the center of the disk, which is our element, is distant x from the center O, that I could have indicated here, of the sphere. I tried to draw this sphere a bit tilted so that you can see that accurately, but I'm going to add a well-drawn picture of this somewhere here or here in the video so that you can be following up along as I am deriving as we are doing the calculations. So this sphere has a uniform density distribution. To set the parameters, we have a sphere of mass capital M, of radius capital R. Here is it. And then the element has a mass, let's say dm, radius of small r, okay? And then x is the distance of the center of the element, so the disk, to the center of the sphere. So the first thing we can do here is to write the expression for the volume distribution of this sphere, as well as that of the element. So if we call that distribution rho, okay, is the mass per unit volume of the sphere. So it's the mass of a sphere over its volume. The volume of a sphere is just 4/3 pi radius cube. But then we can also write this mass distribution in terms of the mass of the element, which in this case is going to be dm divided by the volume of the element. So this element is a disk that has a small thickness dx, so you just take the area of the disk, which is pi small r in this case, okay, because that's the radius of the disk, squared, and then you multiply that times dx. So one thing I need to mention here is that due to the symmetry of a sphere, okay, of the sphere, the moment of inertia about any axis that passes through the center of this sphere is going to be the same. So in this case, I just indicated this axis, but whatever the axis that you decide to take, okay, the moment of inertia of the sphere is going to be the same due to spherical symmetry. So from here, we can write already the expression of dm, okay, which is the mass of our element. So that's going to be 3m on 4 pi r cube times pi r squared dx. You can simplify this further. We are going to have 3m divided by, so the pi's can cancel here, divided by 4r cube, this is a constant, and then times small r squared dx. So this is the mass of the element. And then the moment of inertia of this element, we can calculate it. So the moment of inertia of the sphere, so let's say I sphere, is just going to be the integral, okay, of the moment of inertia of this element, which is the disk. But then in a previous video, we saw that the moment of inertia of a disk about an axis that's perpendicular to the plane of the disk and that passes through its center is given by half times the mass of the disk, Okay, so half I of a disk was half the mass of the disk, and then the distance, and then the radius of the disk squared. So here, since we are having an element of mass dm, and the axis passes through the center of the disk, we can write that the moment of inertia of the element, which is the disk, is going to be half times dm times r squared, the radius of the disk, which is just little r squared. And then we integrate this over the entire mass, okay, in order to get the moment of inertia of the sphere. So this is really the main point of all these calculations, because what's going to follow is just going to be simplifications. So we can replace dm here, so that's going to be the integral of half, okay, times dm, which is, so times r squared first, then times dm, which is 3m, divided by 4r cubed, okay, times r squared dx. Okay, so we can write this again even in a more simpler form, so we can put the constants out of the integrals. Okay, so that's 3m, okay, divided by, we have 2 times that, so that's 8r cubed, then the integral of r to the power 4 dx. Then we need to integrate over all x. Okay, so from this point, in order to perform this integral, we need to either have variables in terms of x only, or variable in terms of r. So we need to choose one variable. So we need to express r in terms of x and then select the variable we want to perform the integration with. Okay, so if you look on this figure, you realize that we have a right angle triangle, okay, like this. So I can make a little sketch here. So you would realize that we are having something like that, and like this. Where here we have x, here we have little r, and here we have capital R. So clearly from Pythagoras theorem, you can see that that capital R squared is going to be equal to little r squared plus small x squared. So we can make use of this expression to simplify further the integral. So if we replace that here, if we replace small r here, we are going to have I of the sphere as 3m divided by 8r cubed times the integral. So here we have r to the power 4, so we are going to have capital R squared minus x squared. This is r squared, and then we add a square here, and then dx. Then we need to do this for values of x that range from negative r to capital R. Because imagine you want to generate the whole sphere, you need to sweep this disk, okay, from negative r. So from this point here, this is negative r to capital R, this point here. So we need to sweep all that like that. Okay, then we need to simplify this integral, and we are going to get the result. So we expand this, we are going to have 3m divided by 8r cubed times the integral from negative r to capital R of r to the power 4 minus 2r squared x squared plus x to the power 4. That's just the binomial expansion of this. Then we integrate, so let's say I sphere, that's going to be 3m divided by 8r cubed times, here we're going to have r to the power 4x minus 2r to the power 2x cubed over 3 plus x to the power 5 on 5. And then we apply the boundaries of integration like that. Okay, so to simplify these, I think I'm going to take another sheet of paper. Just put that like that. Okay. Okay, so to simplify that, we are going to have I sphere equals, so here we just apply the boundaries of integration. We substitute capital R and then negative R. So we have 3m over 8r cubed. So if we substitute the upper bound, we are going to have r to the power 5 minus 2r to the power 5 over 3 plus r to the power 5 over 5. And then minus, we substitute now the lower bound. Okay, we're going to have negative r to the power 5 plus 2r to the power 5 over 3, and then minus r to the power 5 over 5. Okay, hope that's correct. Yeah, that should be fine. Then simplifying, we're going to get 3m over 8r cubed times. So if we simplify this, what we're going to get at the end, I'm just going to give you the result so that it should not be, so that we should not spend too much time on that. So we are going to have here 2 r to the power 5 times 8 over 15. Okay, if we simplify this. So that's equal to 3m. So we can simplify terms. It goes off here. Here you have r cubed. Here you're going to have 2. Okay, you're going to have 3a 1 time and 3a 5 times. So you're going to end up with 2m on 5 r squared. So that's the result we want, which is the moment of inertia of a sphere. So that's 2 over 5 m r squared. Okay. So that's how we can calculate this. Hope everything is clear. Of course, there could be other methods to go about this, but I think this is the easiest one.